Okay, so let's get started. So let me just briefly review what we've covered so far. So in the first lecture, we talked about the basic properties of many-body quantum systems. And then after this, we moved on to think about local unitary operations, and how it is that you can use local unitary operations to construct essentially any unitary. Okay, so this is our discussion of universal quantum computation in the second lecture. Then after this, we asked, well, what happens under a generic computation? Or rather, how should we understand the kinds of quantum states that are generated when you take chains of qubits, illustrated over here, and start allowing them to evolve under 2-qubit unitary operations indicated by these boxes here. So the key point that the kind of key observation that comes out of this is that when you take a bunch of qubits and you allow them to evolve under the logical operations necessary to do your computation, generically what's going to happen is that the state of all of these qubits is going to become highly entangled. Okay, so the point is that if you take a bunch of qubits, let them evolve, the entanglement entropy of a subregion will grow linearly in time. The reason this is important is because the classical memory that is required to represent a quantum state is exponential in the entropy. And therefore, if the entropy grows linearly in time, what this means is that the classical memory required to represent the state is going to grow exponentially in time. Okay, so from that perspective, it looks like quantum advantage is going to be very easy to find, right? From this perspective, you can see that, okay, well, all I have to do is evolve my qubits under a bunch of operations, and quickly it's going to cost exponential memory to do the same thing on a classical computer. But that's kind of not all there is to it, right? So, and that's the topic for today. So the point is going to be that although most quantum states are hard to represent in a classical computer, because they are highly entangled, most quantum states are also totally useless as computational tools. That is to say, if you have a quantum state and you want to get some information out of it, then typically it's going to take you exponential time. Okay, so today is really going to be about measurements. How do you get information out of a quantum state? And so the first thing we're going to talk about is, well, we're going to talk extremely informally about some complexity classes. And then we're going to address a point which somebody told me is on the header of Scott Arrington's blog, which is basically that just because a quantum computer can in principle represent a superposition of many different classical computations, that doesn't mean it's useful for computation. The reason for that is that measurements are random. Okay, so after talking a little bit about how the randomness of quantum measurement really limits the power of a quantum computer, we're then going to talk about typical quantum states, which are just random quantum states. These are going to be highly entangled, but they're also going to be totally useless. And then I'm going to talk briefly about random circuit sampling, this famous experiment from Google in 2018 or 19, where they declared what was then called quantum supremacy. Okay, so let's get started. And please do stop me at any point through the class if you have questions. Okay, so let's go really informally through NP and BQP. Okay, NP is a complexity class, non-deterministic polynomial time, very kind of confusing name. So the idea is basically this. They're computational problems where if somebody tells you the solution, offers you a solution to the problem, and it is a solution to the problem, you can verify that it's a solution efficiently, okay? So a key example is factoring primes. So if you have some large prime number, it's typically very hard to find its prime factors. Sorry, if you have a large number, it's typically hard to figure out whether that number is or is not prime. But if you're given all of the factors, you can then, multiply them together efficiently to reconstruct the number, okay?
Determining if it's prime is actually not hard.
Let's see. So
it's hard.
Determining if it is prime.
Yeah.
So to determine if it is prime, what is your efficient algorithm?
That is this randomized algorithm. There's also a famous paper from 10 years ago called prime QP.
Oh, I see. Okay, so you say it's just if you have a very large number, finding all of its prime factors is the hard thing.
Yeah.
I see.
Determining if it's prime.
Not determining if it's prime.
Yeah.
Okay, right. Okay, interesting. Thanks. Okay. Okay, so determining if it is determining the prime factors of a large number is it's easy to check that you have the right prime factors because, okay, yeah, as we now know, if you're given all of these different prime factors, you can check if they're prime efficiently, and then you can multiply them all together to reconstruct a number. But the thing about NP problems is that there's no guarantee that you know how to find the solution yourself, right? You can verify the solution, but you can't necessarily find it yourself. Now, BQP, loosely, is basically the things you can do in polynomial time on a quantum computer, okay? So let's compare BQP to, say, P, which is the class of problems you can solve efficiently or rather in polynomial time on a classical computer. The reason we believe quantum computers are more powerful than classical computers is essentially because we know that there is an NP problem inside BQP, which is factoring primes. Sorry, finding the prime factors of a large number. Okay, but loosely, NP is a class of problems where you can verify the solution if you're given it. But there are some very hard problems, so-called NP complete problems in NP, where if you knew how to solve them, you'd be able to solve everything else in NP. BQP, things you can do on a quantum computer, we do not expect that NP complete problems live within BQP. Okay, there are just some NP problems inside BQP, like finding the factors of a prime number. So that's okay. Let me just write this over here. So NP solution can be verified in polynomial time. BQP roughly can solve in poly time. But when I talk about polynomial time, I'm always talking about a polynomial in the number of kind of bits that define the problem. Well, here it's number of qubits. Okay. We believe that BQP is larger than the class of problems that you can solve efficiently on a classical computer because of Shor's algorithm. Basically, you can you can find the prime factors of a number efficiently with a quantum computer, but not with a classical computer. But we do not believe that NP is inside BQP. Okay. So this is basically to say that your quantum computer cannot solve NP complete problems. We do not expect a quantum computer can solve NP complete problems. NP complete problems are very hard. If a quantum computer could solve these problems, that'd be fantastic. But we have no reason to believe that they can. Okay, so the important thing, and this is an observation in a paper from Scott Aronson about 20 years ago, is that if you take a quantum computer and you kind of forget that measurement outcomes in quantum mechanics are random, that is to say, you imagine you go to perform a measurement on a quantum state, and you can just sort of pick which outcome you want, rather than getting something that's random determined by Born's rule. In that kind of version of quantum mechanics, that modified quantum mechanics, where you can do this so-called post-election procedure, you get to something called post-BQP. So this is quantum mechanics without the randomness of measurement outcomes, and then you can show that NP is inside post-BQP. In fact, post-BQP turns out to be another complexity class called PP, but I won't go into that in too much detail. So basically, the point is that if you neglect the randomness of measurement outcomes, you're going to find that quantum computers are much, much more powerful than they really are. Okay, that's why it's important to think about the randomness of quantum measurements. So I'm just going to sketch why this is very briefly. The proof is pretty short. So here's the basic idea. So imagine you have a bit string. Okay, so this is it's length n. So now, okay, let's imagine we're trying to solve some NP complete decision problem. Okay, so what that means is that there's some function phi of x. This is our checker function. So phi of x is equal to 1 if x is solution, and it's 0 if not. So here's a kind of, let me just give you a quick example of a NP complete decision problem, so this doesn't seem too abstract. Let's talk a little bit about graph coloring, okay? So graph coloring is where we take some graph, which is a bunch of nodes, like 3 coloring. Okay, so these are like nodes. And this, I'm going to, okay, 3 coloring. So the question is basically, given a graph, which is a bunch of nodes connected by edges. The question is, can I color each of my nodes red, green, or blue, such that there are no red neighbors and there are no like neighbors of the same color, okay? So that is to say, I want to color things so that, e.g., red node has no red neighbors. Okay, now this is really easy to check, right? So let's imagine I've given you a graph and I say, okay, well, here's a coloring of the graph, okay? You can look at that, which happens to be a solution. I can give you a coloring of the graph, probably not this graph, such that, everything is colored red, green, or blue. Red has no red neighbors, blue has no blue neighbors, and green has no green neighbors. By looking at this graph, you can say, oh, well, clearly this works, right? I can just look at all the nodes, check their neighbors, and easily see that I have a solution, okay? However, finding that solution can be pretty hard. So you should think of phi as this, right? So phi takes as input like the set of colors, and it says 1 if you have found a successful assignment of the colors to the different nodes, such that a given color has no neighbors of the same color, and if you return 0 if it doesn't work. Okay, so we have access to this function. So the point then is that, well, a quantum computer allows you to do everything in parallel, right? So let's now imagine that we start off with a state that is we start with like the all 0 state, and we apply a bunch of Hadamards. So what Hadamard does is it just turns each of these zeros into 0 plus 1, okay? And so what that means is that when I apply a bunch of Hadamards, then what I'm left with is an equal amplitude superposition of all bit strings. Okay, so I have every possible kind of test, test X that I could try. But now the thing is, okay, we're thinking about some problem that's in NP. So if we have some way to compute 5x, okay? We know how to compute this. So why don't we just take some extra bit and compute this function for each of these x's, right? So what we're going to do is we're going to bring in some extra ancilla qubit. Let's call this the solution qubit. Probably that's not the best name, but anyway. So we'll imagine we have this extra 0, which is our solution qubit. And now what we're going to do is apply basically a controlled phi operation. So for each x, we now just compute phi and we store it in this qubit here. This is something that we can do efficiently by assumption. So this is the kind of C phi, let's call it. Okay, so now let's ask if we can use a quantum computer to solve this problem. To solve this problem when we have post-selection. So here we've taken a superposition of all possible trials, right? We've done every computation in parallel. All of these are stored kind of very compactly, exponentially many computations are stored in parallel in our n-qubit register, and the solutions are all encoded in this extra solution qubit, okay? So now if I can post-select, that is to say, if I can measure this qubit and just get the outcome that I want, then if actually, I should add an extra, okay, because I'm post-selecting here, I need to be a bit more careful. The point is basically going to be that if I can just choose what outcome I get here, I can immediately generate solutions, right? But to talk about that more formally, I actually need an extra qubit. So let's let's do this thing with some additional qubit here and generate a slightly more complicated state. Just so post-selection isn't such a trivial state, isn't so trivial. Okay. So this is basically this is an extremely important point, right? One reason you might think a quantum computer could be extremely powerful is you can just run every computation in parallel, right? So what we're now going to do, we know how to generate that thing. It doesn't take too much imagination to see that we could also generate this state. And so let's say our problem is we're trying to figure out if there is a solution to our decision problem, right? We're trying to see if there is any x that gives us a solution. So what we're going to do is construct the following state. This is just like a normalization factor. And then we'll have, okay, I'm reordering my qubits. So, okay, our question is there x such that phi of x is 1? Okay, is there some bit string so that this solves my decision problem, or is there not? So we take this state, which I've introduced, this is our kind of solution qubit from before. And this is some like indicator qubit. So let's now ask if we can, using post selection, using this extra power that quantum mechanics doesn't really include, can we, solve our decision problem? So it's really simple. So after we compute this, what we do is let's imagine we measure the indicator qubit, but in this kind of fantasy quantum mechanics, we can just choose the outcome we want. So we're going to choose that this outcome is 1, okay? So the point is, so we measure indicator. And now the point is that if there is no x, if there is no bit string for which this is 1, okay, then what we're going to find is, okay, there's nothing for which this thing is, sorry, we're not going to measure the indicator, we're going to measure the solution qubit. Apologies. Okay, we'll measure the solution qubit. If there is a solution to our problem, that is to say, if there is a term in this sum where phi is 1, then after we do this measurement, we're going to end up with a part of the wave function kind of here, and a part of the wave function over here. So let's say there's one solution. If one solution, just to be concrete, and what we end up with is a state that is proportional to okay. So if there's one solution, what's now happened is we end up with this, this extra qubit over here doing the same thing, but this has exponentially small weight compared to this part. So this is the dominant part of the wave function. So if there is a solution, then what's happened is that just by measuring this first qubit and post-selecting, we have got the solution. Okay, we've determined that there is a solution. If there is no solution, then what's going to happen? If no solution, and we measure that this qubit is in state 1, then well, there's nothing over here, right? There's nothing that can contribute over here because this is never 1. There's no solution to the problem. So in that case, what we find is 1, 0, 0. Okay. So now, if there is a solution to this NP-complete problem, then just by doing a measurement, we can then look at the second qubit. If after post-selecting on the first qubit being 1, the second qubit is 1 with high probability, then there's a solution. If it's 0, then there's no solution. So if you give yourself post-selection, your quantum computer is much too powerful. Okay? This thing here, right. So are you happy with the preparation of this sort of thing?
So happy.
Okay. So now what I want to do is basically a control. I want to take this extra qubit here, this like indicator qubit, and I want to do a control to create a control operation that I did over here. So let's say I have this whole thing. I have some circuit that can compute phi of x in parallel on all the different qubits. Now what I want to do is that operation controlled on the state of the indicator?
You found the circuit board?
No. I would not, yeah, so not live. We can discuss this later. But I think the trouble is that okay, so if I was to take, so if we like work with a box that can compute phi, then yeah, let's discuss this at the end. I'm not going to be able to do this live. Okay, but this is the overall point. If you neglect measurement, if you neglect the randomness of quantum measurement, you will find the quantum computer is way too powerful. And this is why quantum advantage is pretty tough to find. Like there's Shor's algorithm, there's Grover's algorithm, there's many more recent algorithms that have polynomial speedups like Grover's algorithm, but the number of algorithms that have a clear exponential speedup like Shor's algorithm, well, they're pretty scarce. Okay. So are there any questions up to this point? Okay, last thing I'll say, just because this is drawn from this paper from 2005, I think. There's some other very fun stuff in here where Scott Aronson talks in more detail about so-called fantasy quantum mechanics, where he shows that if you change the Born rule even a little bit, then also you'll find that quantum mechanics is more powerful than it should be, right? If you imagine the Born rule was like wave function to 4 instead of wave function squared, then it's going to turn out that you can again solve NP complete problems and more. Okay. Anyway, this is what I worry about measurement. Now let's talk about what happens to general quantum states, okay? So now we're going to take a quantum state that is generated by a generic unitary, and we're going to ask why this thing is so useless. Okay, so there's now going to be a little, I'm going to show you a little technical tool that's going to be very useful. I'm just going to give you one formula that we're going to use throughout. So in order to talk about random quantum states, we're going to need to define what we mean by random, right? We're going to have to define, what we're going to do is we're going to think about states of psi. On n qubits that have this form. Okay, where this is a so-called random unitary. And so I'm going to think about U being so-called H random. Now what that means is basically that U is drawn from a distribution that is invariant under left or right multiplication. Sounds pretty abstract. What that means is the following. So it means that if I take I need to define some measure of the space of unitaries. So think of this as like something like a probability density for a particular giant random unitary. So remember, this thing is d by d with d equals 2 dn. So this is like some probability density. And then I'm going to have some function of u and also potentially this conjugate. Let's draw the DAG. Okay. So what H randomness means is basically the probability density is invariant under left or right multiplication. So one way of saying this, sorry, is like imagine you have, imagine you're doing an integral over like a sphere, right? So this would be the infinitesimal volume element around a particular coordinate, right? So you pick a coordinate. Now a coordinate is a unitary. We're integrating over the space of all unitaries. This thing is like the small volume element around the unitary. So it has this key property. This thing is invariant under left or right multiplication. And, actually, give me just a second here. Okay, so this is the key property. The point is that the volume element is invariant under left or right multiplication by some other unitary. So Hart random uniseries show up everywhere in the quantum information literature. Here we're just going to use one key property of them. We're just going to use the so-called second moment over the Hart distribution, which is going to be some property of the average of two copies of U and two copies of its conjugate. I'll just give you the formula for that and then multiply it a bunch of times. So the point is that this kind of invariance property immediately allows us to write down a huge number of properties of these U's. I'll just give you the one now that we're going to use. So the one property that we're going to use is so when I write like an average, it means an average with respect to this measure. So let's take some unitary U. Let's write down, I'm going to write this in terms of indices. So let's call this I1, J1, I2, J2. This is going to be called like I bar 1, J bar 1, I bar 2, J bar 2. Okay, and what this really means is like an average over the measure. And this thing has a very simple form. It's just this thing. So you get it by like pairing indices up, right? And you need to pair indices up in order to get something invariant. So in the first term, I'm just going to pair these. So that's like pairing these indices together. And I'll pair the other indices too. I2, I bar 2, delta J2, J bar 2. Plus, yeah, so there's going to be a bunch of terms here. I1, bar, I2, bar, J. Sorry, I2. Okay, actually, you know what? Okay, you're gonna have to give me 2 minutes while I write this down. So while I'm writing all of this down, think of some good questions for me. And then there's going to be some other terms which correspond to kind of the other index contraction. We're not going to need to use all this formula in all of its gory detail, but you can just think of it as something over different ways of pairing indices. And then you'll be able to reproduce some of the calculations that I show you having copied this down without too much difficulty. So now, okay, I want. And let's be I1 2 bar. Right, sorry. Okay, so this is a huge expression that tells you basically how to average over this is the second moment of the Hart group. And this is all you need to at least get a kind of heuristic understanding of what's going on with random quantum states. Okay, so basically what I'm doing here, it looks kind of abstract, and not that I've memorized this whole thing. So the point is basically that in this term here, with this larger proof factor, where D is the over a Hilbert space dimension, what I've done is I've like paired these indices with these and those with those, and the same as required by symmetry. And here I've like paired up first indices in a different way to the second indices in one of the two terms. And that's where all of these different terms come from. Okay. Now, okay, having defined the second moment of the Hart group, we can now start talking about what the properties of Hart random states. So, one thing you might want to know is basically how do typical states look in Hilbert space? So there was this picture I drew last time, which I reproduced now. basically about what happens when you just let your state start evolving. So Hilbert space is this, big horrible thing with a few kind of comprehensible states you can write down. This is comprehensible, maybe, this is all 0 and this is all 1 or something like that. You start evolving these things under unitary, and what's going to happen, so this is like Hilbert space. Okay, you kind of, under time evolution, you kind of wander into this bulk of Hilbert space, which is totally featureless, right? And wherever you start, you're going to end up somewhere different. But all of these different states in the middle, kind of in the middle, meaning like typical, they're going to look basically the same to a local probe. And that's going to be basically, that's part of the reason why, quantum advantage is pretty hard to find. So I mentioned in one of the emails, this paper, which really goes into these problems in much more detail, called Most Quantum States Are Too Entangled to Be Useful as Computational Resources. We're going to here look at this statement in a kind of loose way. And we're not going to go into nearly as much detail as they did in that paper, which would require multiple lectures. Okay, so, basically, where do we end up? We start running up on a computer, we're not very careful about how we design the gates. They're noise-free, but, which unitaries we apply, who knows? So you end up here. What do these states look like? First point, they're going to be highly entangled, okay? So we can actually see that using this formula. That's going to be the first thing we try. So first statement, most states are highly entangled. And to see that, we don't have to do too much work. So one measure of entanglement that we've looked at is the von Neumann entropy. Where rho A here is going to be the reduced density matrix of our pure state psi, which is R random. And then what we're going to do is define this other quantity called the Renyi entropy, second Renyi entropy. So this is second Renyi. So that second Renyi is defined in this way. So it's minus log trace rho A squared. Okay, there's another measure of entanglement. It has a less clear meaning in terms of communication resources, the von Neumann entropy. But what we're basically going to want is that the von Neumann entropy is always greater than or equal to the second Renyi entropy. Okay, and what we're going to now ask is what is the average? What we want to know is like the average von Neumann entropy, right? We would like to know the average of this thing, and the following chain of inequalities is pretty useful. So we want to know the average of this. Clearly, it's greater than or equal to the average of the second Renyi entropy. This you can sort of check. It follows, I think, from just the properties of the logarithm. Basically, and then the last part we're going to use is back to this thing. So I should use angular brackets here as I did before. So I want to know the average von Neumann entropy in Hilbert space. I know this is greater than or equal to the average Renyi entropy, and this thing is greater than or equal to minus log of the average so-called purity. Now, why am I doing all of this? The reason I'm doing all of this is that averaging the von Neumann entropy is kind of hard. Averaging the Renyi entropy is also hard because of this log. But averaging the purity is pretty easy because rho is given by just tracing out psi. So rho here involves 2 factors of u and 2 factors of its conjugate, right? So you can actually compute this thing on the left just using this big horrible formula.
Can you write down the relationship between the Renyi entropy and the Shannon entropy?
Von Neumann entropy, I mean, yeah. Yeah, so here's but you mean the general expression for Renyi entropy?
It seems like kind of random, like you've done this inequality.
Oh, I see. Okay, so
That's fine.
yeah, so this is basically, I think this is basically Jensen's inequality at the end of the day.
Oh, I think you can just show it's the alpha where any entropy are monotone and all that.
Yeah, you can, but I think that is essentially just inequality.
Yeah. And then that last inequality is just.
That is also just inequality, yeah. So yeah, this is, yeah, this is, okay, lots of gens. See, we could be here. Okay, so we've got a lower bound, now we have a lower bound on the one over entropy. And we can calculate this thing over here using this formula up here. Let me just sketch roughly how that goes. So the point is that, okay, rho A here, trace rho A squared is, let's just write this down in terms of indices to be super explicit, right? So first off, we need to write down, get this right, rho A, I, J, rho A, J, I, with a sum of I and J. And then rho A here, IJ, this is just, so these are indices within A, so I'm going to indicate them with a little subscript A. This thing here is just coming from tracing out the bigger pure state. So we have U acting on U, so okay, we had U, we have psi. So psi here is these are like indices in A and indices in B. Okay, so given that this is psi, just from the definition, we just took the all zero state and involved it under this big unitary. This is a row index, this is a column index. By doing the partial trace, you can write this row A in terms of this unitary here. And then you'll end up with an expression here, which depends on two U's and two U stars. Inserting this formula into it, what you find immediately is that trace rho A squared is proportional to, it's basically going to be equal to 1 over dA plus ... Where here I'm really working in the regime where kind of A consists of a number of qubits NA, which is less than NB, and that's the condition under which this part is small. But this is the basic point, okay? So the purity is 1 over the Hilbert space dimension of A, but the Hilbert space dimension of A here, this is like 2 to the minus NA, right? So if the purity is exponentially small in the size of the subregion, then when we take the logarithm of this thing over here, we get something extensive. So what that means is that this thing here is like NA in units of bits. Okay? So using this expression for the average of the unitaries, just plugging it into this expression, you'll find that the purity of a subregion is extensive, right? It's the size of the subregion, and this is like NA plus ... But the maximum possible von Neumann entropy is NA. Okay? So this thing here, we also know S of rho A. This is also less than NA. So from this analysis, this quick calculation, which I recommend you do as an exercise, it'll give you a lot of understanding of basically how to manipulate random quantum states. What you get from this is a two-sided bound on the von Neumann entropy, telling you that it's extensive. Okay, and I told you that the classical memory required to represent a quantum state is exponential in its memory using a tensor network. So this tells you the typical quantum states require exponential classical memory to write down. That's the tensor networks. In other words, most quantum states are highly entangled. Okay, so most quantum states are highly entangled. So we've covered why quantum mechanics is hard to represent in a classical computer for typical states. The next point is to show you not only are most states highly entangled and therefore hard to represent, most states are also totally useless. So let's now talk again about measurements. Are there any questions up to the about these?
Do you have the next order correction is?
Yeah. Well, okay, I can sketch you the curves and see what it is. So the point is that because this is an overall pure state, the von Neumann entropy of the entropy of A can only be, if A is more than half of the system, then because the entropy of A is equal to the entropy of B, then you're going to find that the entropy starts increasing, right? So the curve is like this, sorry, for those of you online, I'm sorry, this is going off screen, but the point is basically that if you look at the one node entropy of row A, and you change the number of qubits, so this is NA, and this is the total number of qubits. So this is for a random state, you get this kind of famous page curve. So the one node, if you have 0 qubits, it's 0. If you have n qubits, well, the state is pure, so it has to be 0 as well. And then what happens is that you get some curve that looks like this. This is a page curve. So the point is that when NA is less than half of the system size, then the von Neumann entropy is just increasing linearly, so it's extensive. Okay. Right. Okay. So, but if you're very interested in the subfield interactions, you can get the exact result from just plugging this formula into this minus log of the average impurity. Okay, so why quantum state is useless? Okay, why I say quantum state is totally useless? Well, the reason is that when you look at one of these quantum states, like locally, if you like try to read out some information, you're just going to find nothing. Like a quantum state is going to look like a random number generator. That's the basic problem. So that might be a little bit. Okay, so this is going to be a little bit abstract, but let's suppose we took our initial state, we ran some unitary operation that took us to a typical state, which we'll call psi. And then what I want to ask is basically, well, how long does it take me to determine a property of psi? Or what do I mean by a property of psi, right? So an expectation value, let's say. So one property of psi would be like how is the operator? Okay, this is a property of psi, right? An observable property of psi. Okay. Now, what I'm going to say in the following is going to apply to basically all so-called local properties. So, like I could take Z, or I could replace this with like Z1, Z2, Z3, Z4, or something. You know, this is basically what I get when I measure bit J, right? I look at bit J, and when I look at the J bit, of course, what I see, and I'm measuring, I see an eigenvalue of the observable that I'm measuring, right? So I see an eigenvalue of Zj, it's plus or minus 1, okay? So it looks like I'm getting some information out of my state. But the point is that in a random quantum state, the fluctuations in the signal that you're getting when you do these measurements are exponentially larger than the average value, okay? So what you want to do is determine this. And what I just want to ask, well, okay, how long does it take me to determine a property of psi? How long does it take me to read out some information from this state? So this is just some observable property. And so the question is, you know, how long does it take to get? So we know how to do this kind of calculation. Well, the mean is just the expectation value. And the variance okay. So if I do my experiment, let's say I do my experiment R times. The R repeats of the experiment gives me a result that looks like the mean plus fluctuation mean plus like square root of this variance and the fluctuations go down as the square root of the number of runs, right? So now how large do I need R to be in order to wash out the fluctuations and thereby see the signal? Okay, so first observation, we're dealing with a Pauli operator here. So this first part is 1, right? So the z squared is the identity, so this part's just going to be 1. And so given that that part here is 1, what we need to determine is basically the scale of this thing, right? So the first, okay, in order to determine the typical scale of this, we can't look at the, okay, first observation is just like the average of this thing. Let's, but I'm using an overline again because there's lots of double brackets, lots of angular brackets. The average of this thing is just 0. So that's not telling us very much about the typical scale of the expectation value. The reason the average is typically 0 is the state is basically just as likely to be pointing along the plus z as the minus z direction. So if we want to get a sense of the typical scale of this expectation value, what we need to look at is the root mean square. So what is the root mean square value of this dj? Okay. So just to be clear on the context, we imagine we're given a random quantum state, and we want to extract some property of that random quantum state. That random quantum state has some value of this expectation value, right? And we want to just know what's the typical scale of that expectation value for a fixed random state. For that particular random state, typically what's going to happen is that we have an expectation value zj that's of order the plus or minus the root mean square, right? So this is the mean square. This thing typically is going to be the root mean square. Okay, so this thing, it's 2 psi's, each psi depends on some hard random unitary, there's 2 copies of them. You can calculate it using this thing as well. So using exactly the same formula, then what you can show is that this thing here is exponentially small in the system size. So this thing here turns out to be okay. So if this thing is exponentially small, that is to say, in a typical quantum state, expectation values of local observables, they're basically 0 at large n. When we throw this into here, and we ask how large an R we need to make this second term smaller than this term, well, the answer is that we need R much, much greater than 2 to the n. Well, 2 to the n minus 1, something like that. The point is you need a number of experimental runs that is exponentially large just to determine some local property of this state. Let's just call this 2 to the n. I'm sure I messed up those prefactors. Okay, but this is a total disaster, right? It means that you can create all these really complicated quantum states in your quantum computer. These are the things that generically arise when you supply unitaries to them. But if you want to determine any property of one of these states, you have to do a number of experiments that is exponentially large, right? So this is basically why the randomness of quantum measurement is a total disaster, right? Just because every time we do the experiment, we get some random result. To see anything, we're going to have to wait exponential time. So that brings me towards the end of the discussion of why, the structure of typical quantum states. They're super highly entangled and so super hard to represent. But on the other hand, why would you bother representing them? There's almost no information there that you can extract. So what we, what I'll discuss very briefly, just in the last few minutes, is basically sampling problems, right? So what we've learned so far is that if you apply a generic evolution to a quantum state, you get nowhere, or you get somewhere, but you get somewhere that's useless. An algorithm, on the other hand, a quantum algorithm like Shor's algorithm or like Grover's algorithm, these are going to correspond to much more structured unitary evolutions, right? They're going to be these very delicate paths through the many-body Hilbert space that take you from a state that's easy to understand, that's your input, through some hard to represent part of the Hilbert space, and then eventually back to something that's human interpretable that you can read information out from. Okay, so you have to designing quantum algorithms is somehow about finding these paths through Hilbert space that you can't follow on a classical computer. So a totally orthogonal way to understand the power of quantum computation is to ask, well, what is the task that a random quantum state is good for, okay? So quantum algorithms, very highly structured. You have to be very careful with the unisaries. A totally orthogonal angle on the whole thing is to say, well, if I just get some random quantum state that I get that is generated by a generic choice of unitaries, what property of that quantum state is actually kind of beyond a classical computer? And so this takes us into a discussion of random circuit sampling and the Google supremacy experiment. Okay, so let's see. So far, yeah, we've done. So this part's covered. This part's covered, and now you're reaching the last part. Okay, the idea is this, right? So quantum states generically super highly entangled, can't write them down, they're locally featureless, they're just random number generators. So why not just treat them as random number generators? Why not just ask, okay, well, why don't I just use my quantum computer as a random number generator? And the point is going to be that actually the distributions that you end up sampling from when you use quantum computers in this way are actually hard to sample from using a classical computer. So this is random circuit sampling. Okay, so I mean, I said a moment ago that the quantum state just looked a bit like a random number generator. That's not quite right, or at least it is a random number generator, but not an uncorrelated random number generator. Let's think about that in a bit more detail. So imagine I've got n qubits, right? They're represented by these little spheres. So here's my n qubits. Now, one kind of random number generator is where I say each of these qubits is like randomly up or down, right? Each of these they're uncorrelated with each other. Each of the the qubit is going to be 0 with probability 1/2 and 1 with probability 1/2. Or more generally, we say these are just totally random single qubit states. So for example, I might say each single qubit state is like cosine theta over 2 0 plus sine theta over 2 some phase. Okay. So if we do the uncorrelated case first, then let's just look at the corresponding probability distribution. So I'm going to take it, let's say this is a single qubit state, psi 1. And now let's imagine I take some quantum state of n qubits, it's the tensor product of independent single qubit states, each of them random, okay? And I want to ask, okay, well, if I just start measuring this state, from which probability distribution am I sampling? If I measure in Z basis, what I'm sampling from is a probability distribution over bit strings that is just defined by the wave function. Okay. And so the key point is that, okay, first off, these are random states. So the probability that if I look at if I can average psi over all different choices of the unitaries, I average over all of these like tensor products of single qubit states, what I'll find is that the probability, clearly the average is going to be 1 over 2pn, right? On average, I mean 1 over 2pn, right? So there's too much existing chalk. So I'm equally likely, if on average, I'm equally likely to see any particular bit string. Now, okay, we're going to come to our third application of that formula in a moment. So if we apply it to the single qubit case, then, okay, what I want to ask now is not just what the average is. I want to ask about the structure of this probability distribution. So that is to say, I want to think about like the distribution of probability distributions over states. So a natural thing to look at is the second moment of the distribution, okay? So this is an average over U of this object. And so what you find in the single qubit case, by applying that formula or using other simple strategies, is that this probability, this goes as 2/3 to the n, okay? So still, still exponentially small. But what about a Haar random? What about a Haar random set of n qubits, a highly entangled state? So for my highly entangled state, if I do the same calculation, well, okay, first off, the second moment is very simple. It's again one of it is the n. Okay, that's the move. So it's again one of it is the n. But now I want to ask again, what about the distribution of possible p's? So if I calculate this thing, again, using the same formula involving u over there, then what you'll find is that this as this one, okay? So, okay, what's the significance of this? So, what we're seeing here is that the average of the square is going as 1 over 2 to the n, compared with the uncorrelated distribution that is going as 2/3 to the power of n, right? So as I increase n, this thing decays much more slowly than this thing. What this means is that if I look at the kind of distribution of probabilities, then there are for Haar random U, there are very few bit strings with so-called heavy weight. Okay, large weight meaning high, probability that I see them. So that means Haar random states represent a pretty weird scenario where essentially there's no state, no bit string that you're likely to see, right? All bit strings are very, very unlikely. Whereas here, there can be some bit strings that are much more likely than others. So this like confinement of the probability distribution is really a key feature of these random quantum states. And in fact, a more sophisticated calculation will show you that the distribution of these probabilities follows the so-called Porter-Thomas distribution. Okay, so I want to ask about the probability for a given probability of a probability, right? This is the kind of Born probability, and I'm asking about the distribution of these things over the ensemble of U's, right? So this probability turns out to decay with a characteristic form which is up to normalization. And we'll figure that out in a second. This is a Poisson distribution, so let me just, who's quick at integrating? I guess it's just D. Okay, so what this means that and D here is to the end, right? So we have this like extreme confinement of the distribution of probabilities around, in the regime where the probability is of order 1 over B. Okay. Now this is so-called people call this anti-concentration, right? So the distribution is not concentrated on any particular bit string. It is, in some sense, as anti-concentrated as you can be. The state is kind of spread extremely evenly over the Hilbert space when you express it in the basis of these bit strings. Okay, so what random? I mean, now I can, having described the Porter-Thomas distribution, let me just wrap up by talking about what Google did in the supremacy experiment. So what they basically ask is whether they are sampling from this distribution. Okay, that's the problem. So if you have a highly entangled quantum state, that state is characterized by an anti-concentration of this distribution. So the random circuit sampling experiment was aiming to check whether they were sampling from this, right? And so the key metric that they use is the so-called cross-entropy benchmark. So they looked at the so-called linear cross-entropy. We often call it linear XEV. So the linear cross-entropy benchmark is, let's go through the experiment. So here's what you imagine doing. You create your quantum state and then you measure all the bits, right? So every run of the experiment, you get some set of bits. let's call it B vector. So this is like n bits. That's our first run. In the second run, we get another bit string and another bit string. Okay, so as after we run, t experiments, let's say, we have like n, t n bit strings. And so then what they did is, given each of those bit strings, what you try to do is calculate what the probability should have been according to your model. So what is this model? The idea is that you've got a pretty good idea about which state you prepared, right? So you've applied some circuit, taking you from all 0 to u psi, to u on all 0, which is psi. You have some estimate for what this state looks like. And now what you're going to do is, okay, well, given that you've seen these bit strings, what you're going to do is use your model of the system to estimate or P classical B. So P classical B, it is so this is the observed bit string, okay? An observed bit string, and let's call it P model. And this is your model for the state. It could even be a density matrix. The model doesn't have to be pure. But the idea is you take this model for the state that you should have prepared. And now, given these estimates for the probabilities, you calculate linear XEV, which is, in this case, 2 to the n times the average of P model B over, where this average is over observed bit strings, and you take away 1. Okay, so this is just the definition of XEV. The point is basically that if you get the Porter-Thomas distribution, like if these bit strings are actually distributed with the Porter-Thomas, then what you'll find is this is equal to 1 if basically if P model B equals PP equals Porter-Thomas. Okay, so the idea then is that, okay, you're running your quantum computer, you sample these bit strings, you get them pretty efficiently, right? Like every time you run the computation, you get this bit string in a short amount of time. But actually calculating this probability, well, that's really hard. That means you have to write down the quantum state and calculate this thing here. That generically requires memory scaling exponentially with the system size. So the idea was basically you very efficiently get a bunch of these bit strings. That is to say, you're efficiently sampling from the quantum state, because that's, sort of what quantum states do. They just generate random numbers for you when you look at them. And then you invest an enormous amount of classical computational effort to calculate what the probabilities should have been. And then you get this, okay? So that's the basic idea behind random sampling, which was introduced as an idea, I guess, a little under a decade ago now, as a computationally useless task that is nevertheless hard for a classical computer and easy for a quantum computer. So at that point, I'll wrap up. Thank you all for listening, and let me know if there are any more questions.
Might be misunderstanding here, something here. But isn't the most spread out distribution you can have just uniform? And can't a bunch of pattern markets do that?
Oh, good question. Okay, so yeah, okay, you're absolutely right. Yes, sorry. So if you take it all 0 state and you apply random pattern models, you prepare a product state in the X basis, right? So then, yeah, if you measure in Z basis, you get probability 1 over 2 to the n of every individual bit string. So you're absolutely right. But the point is also with the Hadamard, you could just change your basis to measure in the X basis, then you have no concentration. So the key point with the Haar random states is that they're anti-concentrated in all local bases. Sorry, yeah, thank you for the question. That's an important point. Okay, if there are no more questions, then we can wrap up. I'll answer your question about how you actually prepare that phi state now. But yeah, those of you listening on Zoom, thanks for joining.